This lecture is about the implementation of text retrieval systems. In this lecture, we will discuss how we can implement a text retrieval method to build a search engine. The main challenge is to manage a lot of text data and to enable a query to be answered very quickly and to respond to many queries. This is a typical text retrieval system architecture. We can see the documents are first processed by a tokenizer to get tokenized units, for example, words. And then these words or tokens will be processed by an indexer that would create an index, which is a data structure for the search engine to use to quickly answer a query. And the query will be going through a similar processing step. So the tokenizer would be applied to the query as well, so that the text can be processed in the same way. The same units will be matched with each other. And the query representation would then be given to the scorer, which would use the index to quickly answer a user's query by scoring the documents and then ranking them. The results will be given to the user. And then the user can look at the results and provide some feedback that can be explicit judgments about which documents are good, which documents are bad, or implicit feedback such as click-throughs. So the user doesn't have to do anything extra. The user would just look at the results and skip some and click on some results to view. So these interaction signals can be used by the system to improve the ranking accuracy by assuming the viewed documents are better than the skipped ones. So a search engine system then can be divided into three parts. The first part is the indexer, and the second part is a scorer that responds to the user's query, and the third part is a feedback mechanism. Now, typically the indexer is done in the offline manner, so you can pre-process collect the data and to build the inverted index, which we will introduce in a moment. And this data structure can then be used by the online module, which is a scorer, to process a user's query dynamically and quickly generate search results. The feedback mechanism can be done online or offline, depending on the method. The implementation of the indexer and the scorer is fairly standard, and this is the main topic of this lecture and the next few lectures. The feedback mechanism, on the other hand, has variations. It depends on which method is used. So that is usually done in an algorithm-specific way. Let's first talk about the tokenizer. Tokenization is to normalize lexical units into the same form so that semantically similar words can be matched with each other. Now, in a language like English, stemming is often used, and this is to map all the inflectional forms of words into the same root form. So, for example, computer, computation, and computing can all be matched to the root form compute. This way, all these different forms of computing can be matched with each other. Now, normally, this is a good idea to increase the coverage of documents that are matched with this query, but it's also not always beneficial because sometimes the subtle difference between computer and computation might still suggest the difference in the coverage of the content. But in most cases, stemming seems to be beneficial. When we tokenize the text in some other languages, for example, Chinese, we might face some special challenges in segmenting the text to find the word boundaries, because it's not obvious where the boundary is, as there's no space to separate them. So here, of course, we have to use some language-specific natural language processing techniques. Once we do tokenization, then we would index the text documents, and that is to convert the documents into some data structure that can enable fast search. The basic idea is to pre-compute as much as we can, basically. So the most commonly used index is called inverted index, and this has been used in many search engines to support basic search algorithms. Sometimes other indexes, for example, a document index, might be needed in order to support feedback. Like I said, and this kind of techniques are not really standard in that they vary a lot according to the feedback methods. To understand why we want to use inverted index, it would be useful for you to think about how you would respond to a single term query quickly. So if you want to use more time to think about that, pause the video. So think about how you can pre-process the text data so that you can quickly respond to a query with just one word. Well, if you have thought about that question, you might realize that, well, the best is to simply create a list of documents that match every term in the vocabulary. In this way, you can basically pre-construct the answers. So when you see a term, you can simply just fetch the ranked list of documents for that term and return the list to the user. So that's the fastest way to respond to a single term query. Now, the idea of inverted index is actually basically like that. We're going to pre-construct such an index that would allow us to quickly find all the documents that match a particular term. So let's take a look at this example. We have 3 documents here, and these are the documents that you have seen in some previous lectures. Suppose we want to create an inverted index for these documents. Then we would maintain a dictionary. In the dictionary, we'll have one entry for each term, and we're going to store some basic statistics about the term. For example, the number of documents that match the term, or the total number of total frequency of the term, which means we would count the duplicated occurrences of the term. And so, for example, news, this term occurred in all the 3 documents, so the count of documents is 3. And you might also realize we need this count of documents or document frequency for computing some statistics to be used in the vector space model. Can you think of that? So what weighting heuristic would need this count? Well, that's the IDF, right? Inverse document frequency. So IDF is a property of a term, and we can compute it right here. So with the document count here, it's easy to compute the IDF either at this time or when we build the index, or at running time when we see a query. Now, in addition to these basic statistics, we also store all the documents that match the news. And these entries are stored in a file called postings. So in this case, it matched 3 documents, and we store information about these 3 documents here. This is the document ID, document 1, and the frequency is 1. The TF is 1 for news. In the second document, it's also 1, etc. So from this list, we can get all the documents that match the term news. And we can also know the frequency of news in these documents. So if the query has just one word, news, and we can easily look up this table to find the entry and go quickly to the postings to fetch all the documents that match news. So let's take a look at another term. This time, let's take a look at the word presidential. Right? This word occurred in only one document, document 3. So the document frequency is 1, but it occurred twice in this document. So the frequency count is 2. And the frequency count is useful in some other retrieval method where we might use the frequency to assess the popularity of a term in the collection. And similarly, we'll have a pointer to the postings right here. And in this case, there is only one entry here because the term occurred in just one document, and that's here. Right? The document ID is 3, and it occurred twice. So this is the basic idea of inverted index. It's actually pretty simple. right? With this structure, we can easily fetch all the documents that match a term. And this will be the basis for scoring documents for a query. Now, sometimes we also want to store the positions of these terms. So in many of these cases, the term occurred just once in the document. So there's only one position, for example, in this case. But in this case, the term occurred twice, so we would store 2 positions. Now, the position information is very useful for checking whether the matching of query terms is actually within a small window of, let's say, 5 words or 10 words, or whether the matching of the 2 query terms is in fact a phrase of 2 words. So this can all be checked quickly by using the position information. So why is inverted index good for faster search? Well, we just talked about the possibility of using it to answer a single word query. And that's very easy. What about the multiple term queries? Well, let's first look at some special cases of the Boolean query. A Boolean query is basically a Boolean expression like this. So I want the relevant document to match both term A and term B. Right? So that's one conjunctive query. Or I want the relevant documents to match term A or term B. That's a disjunctive query. Now, how can we answer such a query by using inverted index? Well, if you think a bit about it, it will be obvious, because we can simply fetch all the documents that match term A and also fetch all the documents that match term B, and then just take the intersection to answer a query like A and B, or to take the union to answer the query A or B. So this is all very easy to answer. It's going to be very quick. Now, what about the multi-term keyword query? We talked about the vector space model, for example, and we would match such a query with a document and generate a score. And the score is based on aggregated term weights. So in this case, it's not a Boolean query. But the scoring can be actually done in a similar way. Basically, it's similar to disjunctive Boolean query. Basically, it's like A or B. We take the union of all the documents that match at least one query term, and then we would aggregate the term weights. So this is a basic idea of using inverted index for scoring documents in general. And we're going to talk about this in more detail later. But for now, let's just look at the question, why is inverted index a good idea? Basically, why is it more efficient than sequentially just scanning documents? Right? This is the obvious approach. Right? You can just compute the score for each document, and then you can then score them. You can then sort them. Right? This is a straightforward method, but this is going to be very slow. Imagine the web; it has a lot of documents. If you do this, then it would take a long time to answer your query. So the question now is, why would the inverted index be much faster? It has to do with the word distribution in text. So here's some common phenomena of word distribution in text. There are some language-independent patterns that seem to be stable. And these patterns are basically characterized by the following pattern. A few words, like the common words like the, or we, occur very, very frequently in text. So they account for a large percent of occurrences of words. But most words would occur just rarely. There are many words that occur just once, let's say, in a document, or once in a collection. There are many such singletons. It's also true that the most frequent words in one corpus may actually be rare in another. That means, although the general phenomenon is applicable or is observed in many cases, the exact words that are common may vary from context to context. So this phenomenon is characterized by what's called a Zipf's law. This law says that the rank of a word multiplied by the frequency of the word is roughly constant. So formally, if we use f of w to denote the frequency, r of w to denote the rank of a word, then this is the formula. It basically says the same thing in just mathematical term, where c is basically a constant, right? And there is also parameter alpha that might be adjusted to better fit any empirical observations. So if I plot the word frequencies in sorted order, then you can see this more easily. The x-axis is basically the word rank, and this is r of w, and the y-axis is the word frequency, or f of w. Now this curve basically shows that the product of the two is roughly the constant. Now if you look at these words, we can see they can be separated into three groups. In the middle, it's the intermediate frequency words. These words tend to occur in quite a few documents, right? But they are not like those most frequent words. And they are also not very rare. So they tend to be often used in queries. And they also tend to have high TF-IDF weights, these intermediate frequency words. But if you look at the left part of the curve, these are the highest frequency words. They occur very frequently. They are usually stop words, like the, we, of, etc. Those words are very, very frequent. They are in fact too frequent to be discriminative, and they are generally not very useful for retrieval. So they are often removed, and this is called stop words removal. So you can use pretty much just the count of words in the collection to kind of infer what words might be stop words. Those are basically the highest frequency words. And they also occupy a lot of space in the inverted index. You can imagine the posting entries for such a word would be very long. And then therefore, if you can remove such words, you can save a lot of space in the inverted index. We also show the tail part, which has a lot of rare words. Those words don't occur very frequently, and there are many such words. Those words are actually very useful for search also, if a user happens to be interested in such a topic. But because they're rare, it's often true that users aren't necessarily interested in those words. But retaining them would allow us to match such a document accurately. And they generally have very high IDFs. So what kind of data structure should we use to store inverted index? Well, it has two parts, right? If you recall, we have a dictionary, and we also have postings. The dictionary has modest size, although for the web, it's still going to be very large, but compared with postings, it's modest. And we also need to have fast random access to the entries, because we want to look up the query term very quickly. So therefore, we prefer to keep such a dictionary in memory if it's possible. Or if the collection is not very large, this is feasible. But if the collection is very large, then it's in general not possible. If the vocabulary size is very large, obviously we can't do that. So, but in general, that's our goal. So the data structures that we often use for storing dictionary would be direct access data structures like a hash table, or B-tree. If we can't store everything in memory, we can use disk, but to try to build a structure that would allow you to quickly look up entries. Right? For postings, they are huge, you see. And in general, we don't have to have direct access to a specific entry. We generally would just look up a sequence of document IDs and frequencies for all the documents that match the query term. So we would read those entries sequentially. And therefore, because it's large, we generally store postings on disk. Right? So they have to stay on disk. And they would contain information such as document IDs, term frequencies, or term positions, etc. Now, because they are very large, compression is often desirable. Now, this is not only to save disk space, And this is, of course, one benefit of compression. It's not going to occupy that much space. But it's also to help improving speed. Can you see why? Well, we know that input and output would cost a lot of time in comparison with the time taken by CPU. So CPU is much faster, but I/O takes time. So by compressing the inverted index, the processing files will become smaller, and the entries that we have to read into memory to process algorithm would be smaller, and then so we can reduce the amount of traffic in I/O, and that can save a lot of time. Of course, we have to then do more processing of the data when we uncompress the data in the memory. But as I said, the CPU is fast, so overall we can still save time. So compression here is both to save disk space and to speed up the loading of inverted index.